let's just recall the chain rule for partial derivatives. If w is a function of x and y, which we call f, and x is also a function of two new variables u and v, and y is a function of u and v, then the partial derivative of w, this function, with respect to one of these new variables, namely u, is equal to the partial derivative of w with respect to x multiplied with the partial derivative of x with respect to u. So if we only had one variable, this would be the result. But now we have two variables, so we have to add with this term. The derivative of w with respect to y multiplied with the partial derivative of y with respect to u. And we get a similar expression for the partial derivative of w with respect to v in this form. This chain rule is important for understanding the Laplacian in polar coordinates. You remember that the Laplace operator, the Laplace equation, is when the partial derivative of u with respect, the second derivative of u with respect to x plus the second derivative of u with respect to y is equal to 0. So this is an important equation which we want to transform in polar coordinates. You remember also that if we have some coordinate xy, this coordinate can be described in polar coordinates in this way. X equal to r cosine to theta, and y is r multiplied with sine theta. We are also known by the Pythagoras sentence that the square of r is equal to the sum of the square of x and square of y. Thus we have this expression for r. Moreover, the tangent to theta is equal to y over x. Using the chain rule 2 times, we are able to find that the derivative of u, the partial derivative of u 2 times, that's the second derivative of u with respect to x, of course, is given by this expression. And using the chain rule once more, we end up with this expression for the second derivative of u with respect to x. We now have just recalled what r, the relation between r and x and y, and the relation between theta and x and y. It's given by this. So then we get the derivative of r with respect to x easily, and the derivative of theta with respect to x by this expression. Here we have used that the derivative of arc tangents of u with respect to u is equal to 1 over 1 plus u square. This is a well-known formula. Okay, inserting the expressions into this expression, we obtain finally that uxx is given by this expression. Similarly, we can find that uyy is equal to this expression. If you are unsure about these symbols x, y, and so on, let me just recall that every time when we, for example, say the derivative of u with respect to x, then we abbreviate this by this u index x. And if we take the derivative of u with respect to y, then we just write uy. So now we understand what ux means and also uxx. Okay, so when we have these two expressions for uxx and uyy, we just take add these two expressions to get the Laplacian, and then we get this expression. Thus, in other words, the square of the Laplacian is just the Laplacian of u. That's the same as the square of nabla is given by the partial derivative of u with respect to r 2 times plus 1 over r multiplied with the derivative of u with respect to r plus 1 over r square multiplied with the second derivative of u with respect to theta. So this is the Laplace operator in polar coordinates. If we now add one variable, for example, that we have if we have three spatial coordinates x, y, and z, so that the function u, the unknown variable u, is a function of these three coordinates, then it's really simple to see that we only have to add the second derivative of u with respect to z. And this is called cylindrical coordinates when we have the value of u described by r, theta, and z.